Yeah, we have to yes, it is. The support. Welcome back.
I'm very glad to have Ken Dykema here to give us a mini course, and he will talk on the spectral distributions and the decompositions of operator in finite Neumann algebras.
Thank the organizers for giving me this opportunity. So this is officially a mini course. I'm allowed to start, or at least with some early elementary things. So let's start with a Hilbert space H. And bound operator H. And of course, we know that the spectrum of T set of complex numbers lambda such that T minus lambda times the identity is not invertible. Not invertible. And so one of the main themes in single operator theory is, can we use somehow decompositions of the spectrum to decompose T into simpler parts, to analyze T using the spectrum. And of course, we know very well that if T is normal, right, it commutes with its edge, right? Yes, we have spectral. So for every Borel set, explain, let's say we have the and this actually gives us a projection valued measure. So commuting with T and we recover T as integral over the spectrum of lambda. And this has the property, of course, that the spectrum of T restricted to the range projection of B is contained in B closure. All right. So what if T is not normal? We do? Well, in general, very little. However, if the spectrum is not connected, not connected, we can use the Ries-Dunford functional calculus for open subsets of this, right? So given G a closed subset, is closed and open, the relative topology of the spectrum of T. You take, so here's a picture of the spectrum of T, it has at least two parts. One is G, the other complements several parts, and take a contour, closed contour in complement of the spectrum gamma. In the complement of the spectrum such that line number of gamma around every point of G is 1, and every point of spectrum of T take away G is 0, like the one I've drawn here. And the integral.
Such a map for all of this in the picture, sure, but in general, it doesn't seem all that obvious.
Well, if it's open, I mean, you can put a little neighborhood around it. And then, yeah, so that you can, yeah, it's true. Yeah, you can always do it.
Right. So it's not connected conformation.
It's a closed contour.
Is it simple closed curve or? it has-
Ah, sorry. Right. It can have several pieces. Right. Yeah, it's not a simple closed curve. Right. Yeah, of course. Yeah, if you had something like this and another piece here, and you wanted to G with this piece with the inner piece here, you have to take two. But yeah, of course, yeah. Thanks. Thank you for pointing that out. Right. Well, then you take E T of G, let this be 1 over 2 pi I, the integral around gamma of lambda identity minus T inverse, sorry, Z minus V, and you get potent. So this is the Riemann integral of H value. Integrand, and then Et of G, an idempotent, and here's the P. So the range and also the kernel of Et of G is T invariant subspace, closed subspace. And follows that the spectrum of the restriction of T to this subspace is, so this is the spectrum computed in the sub, and bounded operators on the subspace is contained in, or is actually equal to G. Okay. Right. So you can break things up. And moreover, the reason done for calculus is functional calculus is more general. You put a holomorphic function a neighborhood of the spectrum. That's holomorphic on a neighborhood of the spectrum. You put this in here, and this is then f of t, and it's a functional calculus. It's really nice, but in the particular case, when your function is 1 on a neighborhood of G and 0 elsewhere, you get an idempotent, and so that's all this works. Okay, we have some properties for G1 and G2 cloaked in set. E T of G1, E T of G2 is E T of the intersection. That follows the functional calculus aspect, and if intersection is empty, then ET of the union is and they're commuting with each other. However, of course, this ET of G is not the function. And well, if we start with, we have a finite dimensional Hilbert space, and of course the spectrum of T is finite. That they're distinct. Then ET and the J is just the generalized eigenspace. The union J from 1 to infinity, kernel of T minus lambda J I to the kth power. And we have the non-orthogonal direct sum of H with of lambda 1 direct sum of lambda L sum. So you can choose an invertible operator.
In the image of ET of lambda is this generalized thing?
It should have been H's in here. So there exists a now we're talking about H's algebra. P of H is just an vertical that makes these into an orthogonal direct sum. A inverse looks like a block diagonal matrix. We've got lambda 1 some diagonal first block, here. And 2 is in the second block. And 0 is everywhere else. Of course, if we further analyze, so the star parts here, if you take away the diagonal, these are just nilpotents. And if you further analyze the structure of the nilpotent, you get the Jordan canonical form, which we all know and love. But in any case, we see that so if we let I can write T as A inverse times S, if S is the just diagonal matrix, lambda 1, repeated the appropriate number of times. So here's the diagonal matrix here. T is A inverse S. Oh, maybe I should call it something else. Let's call it N because it's normal. A plus the conjugate of the strictly upper triangular bit, which is what we'll call Q, and Q is going to be nilpotent. And notice that the strictly upper triangular bit commutes with the diagonal bit. So call this whole thing S. See that S and Q commute. Okay. So that's just something to do. Now, of course, you don't need the whole one functional calculus to do this. You can argue directly. I'm sure you've all seen that sort of argument. Now, so what are some takeaways here? We have this nice expression as something similar to a normal operator plus a commuting nilpotent. And another thing to think about is that we have these subspaces, which are somehow the spectral subspaces, but the angles between them don't have to be orthogonal, right? They might have an angle. Okay. Now back to the case of infinite dimensional Hilbert spaces and operators on them. Well, this sort of thing can happen, but it's actually not generic. It's kind of rare, but it's nice to give a name things to nice things when they happen, and to investigate issues around that. So I'm going to let's say a bounded idempotent valued spectral measure is from the Borel that's complex plane through set of idempotents in B of H. Where all set B maps to an idempotent E of B, satisfying first of all E of the whole complex plane of the identity E is 0, and secondly E of intersection two sets, two Borel sets is the product of the idempotents. That entails, of course, that the idempotents commute with each other all. And thirdly, if P1 up P2 and so on are pairwise disjoint, then E of the union is of E of the BNs, where the sum converges in strong operator topology. And fourthly, I guess this is going kind of so.
And it's not just bounded distribution.
It's that they're uniformly bounded to this group. Norm of EB is finite. Okay. Now,
Is that not guaranteed by 1 and 3? And write,
well, no, not in an obvious way, because this is actually an interesting point when you have two subspaces, let's say, and you want to make one of them the range and the other one the kernel. The norm of the EB goes up as the minimal angle between these two subspaces goes to 0. And of course, EB could even be unbounded. You could have the angle equal to 0. Come back later. If the angle between two subspaces, the minimal angle is equal to 0, even though that the algebraic sum of them may be the whole Hilbert space, the corresponding idempotent would have infinite norm operator. But so you could have things of large norm, and then 1 minus EB would have the same large norm, but the sum of them. Now, I'm not quite sure there could conceivably be a clever way breaking things into infinite pieces, but I don't think there is.
This will be assuming positivity.
Right. They're not positive, right? Not necessarily. Okay. Now here, unfortunately, I'm a little bit unclear on the history. There's a paper by Vermeer that came out, I think, in the 50s. Wormer, I sort of pronounce his name even, but he also cites work of Mackey. I'm able to get a copy of, but this said that when you've got bounded idempotent spectral measure, then you can find an invertible that conjugates it into an actual spectral measure, a projection value spectral measure. So there exists, so given an E, spectral measures, there exists bounded invertible A Hilbert space such that for all relevant E, A, E, B, is self-adjoint. Okay. is what we call a projection, self-adjoint idempotent, has norm 1. Okay. Now, Dunford defined a paper that came out in '54. He, a bounded operator on Hilbert space, is a spectral operator if there exists a bounded valued spectral measure E such that mutes with T for all Borel sets B, EB, which entails that the range and kernel of EB are T invariant subspaces. And will be the spectrum of T restricted to the T invariant subspace E, E, H is contained with the convention that this is the zero Hilbert space. Our convention is that all operators on the zero Hilbert space have empty spectrum. Think about the definition of spectrum. Makes perfect sense. Okay. Sounds like a question for George Eliot. Yeah. What is this? Okay. And then he proved that if you have a spectral operator, then this E, this bounded idempotent value spectral measure is unique. Operator, then E satisfying 1 and 2. And so we write it as bounded idempotent spectral value spectral measure associated with T like that with a subscript T, and for all B lives in the double commutant of singleton set T. So in particular, it lives in the binomial algebra generated by T. And okay. So spectral operators are really special, and even more special class of them. So T in B of H is of scalar type. Special operator. But as you read E sub T, and then
So scalar type, if you can recover T as the integral.
Idempotent valued spectral measure. So T is equal to the integral. Apparently the operator vanishes. E sub T is 0 outside of spectrum T. And then so if we write T as the integral of lambda T lambda, where this is, I'm converging in the norm. So I guess if you take the directed set, all the finite partitions, 4L subsets, and that converges. Sorry, what's the question?
This more general spectral operator is the measure supported on the spectrum.
Yeah. Because of this, if you had an invariant subspace and you had some piece of the spectrum outside of that, some spectrum were larger than the spectrum of T, that would be, you would get a contradiction.
Okay.
Well, the upshot is, now if you take this integral and you conjugate by A to make all these self-adjoint, you'd get a normal operator. So the upshot is, an operator is of scalar type if and only if it's similar by an invertible to a normal operator. Exotic, actually. Corollary is that scalar type, if there exists an invertible A at A T inverse, maybe the other way around, is normal. Okay. Recall somebody Q. An operator Q is quasi-nilpotent. If its spectrum consists of only 0, that's the same on spectral radius formula. If when we take the nth power of Q and take the norm of that and raise that to the 1 over nth power, that converges to 0 as n goes to infinity. Now, Dunford proved that if you take a spectral operator and consider its bounded idempotent value spectral measure, then take this integral and then subtract it. Yeah.
One question about the corollary over there. So for finite dimension, why are non-diagonalizable matrices non-spectral?
They are spectral, but they're not scalar.
This requires scalar type. Okay, sorry.
But the theorem you're thinking of is coming right up. So
it says that So if you take a spectral operator, you take its E sub t, and then you take the integral and subtract that off, what you're left with is quasi-nilpotent. So this is inferred. Suppose T is spectral. Let T of lambda bounded idempotent valued spectral measure. Then, of course, S is of scalar type. And T is equal to S plus Q, where Q is quasi-nilpotent. And commutes with S.
This is the converse of this rule.
Yes. Second part of the theorem, conversely, if T equal to F Q with S of scalar type, meeting with that. Then T, then T is spectral. And ET equal to ES. And so really exactly both directions. So yes.
Yeah, so in finite dimension, generically Q is 0. Is there a way to make sense of that in infinite dimension or something like that?
Well, I don't know. It seems to me generically the arrangement dimensional generically operators are not similar to normals, but I don't have a good definition.
Yeah, I guess the question would be generic spectral operators are Q
Or generic spectral operator. I don't know what. Yeah. Okay.
Definition. Let's call it generic.
I think the spectral operators are very special. Although, you know, every when H is not dimensional, every operator is special. Right, so let me just write as sort of a corollary, obvious corollary here. P in B of H is a spectral operator. If and only if it can be written in a form N of Q, where N is normal. Sorry. Only if there exists a such that T is equal such that when we conjugate Q with A, we get N Q and normal Q on the Q condition. So the Q here is not, of course, the same Q here is conjugate Q by Q, but it's still quasi number. So, okay. So spectral operators are very nice, but very special. Unfortunately, there are other classes of operators that are understood where we have some sort of decomposition using spectrum. And these were introduced in the 60s by Voyage and important work by decomposable operators.
Yeah, can I ask a question?
Sure.
If the spectrum is totally disconnected, can I just keep doing that thing you talked about before, the functional calculus, claim that it's a spectral operator?
I know that every operator with totally disconnected spectrum is decomposable. And I don't have in mind the proof. I'm pretty sure it comes from something like that. But I'm not sure you would actually get bounded. Because you have to do the finer and finer partitions. I'm not sure you would get bounded idempotent valued spectrum. Yeah. So okay, so I have some candidates maybe for operators that we could show are decomposable with have totally disconnected spectrum, but fail to be spectral. I think actually that will follow from one of the theorems. Yeah. So oh yeah, fail to be spectral operators. Yeah. Okay, so Chipper and Foyash in theory. P and B of H. Great, I'm not exactly clear on the history because there are many different ways of defining decomposable, and so this may not have been Foyash's original definition. I'm sorry, but one of the equivalent ones. Maybe hard to get. P and B of H is decomposable. Has spectral capacity. And the spectral capacity or T is map from complex plane to the decomposed T invariant subspaces. Of Hilbert space. So we'll denote it by closed set K, closed subspace curly F, it's K. Satisfying properties. First of all, F of the empty set is the zero subspace, and F of the whole complex plane, whole space H. And secondly, if we have a finite cover the complex plane.
Finite open.
Then F, so U1 up to UN is a finite cover, F of U1 closure plus F of U2 closure, etc. Da, 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 plus F of UN closure is the whole space H, where this is an algebraic. So these is dense in H, that is actually range. Thirdly, things happen at countable intersection. F of the intersection of Kn and 1 to infinity is the intersection of F Kn. And fourthly, for K spectrum of the restriction of T invariant subspace. K, again, spectrum taking the boundaries in this space. It means that. So, if T is decomposable, sorry, if T is a spectral operator, taking Fk to be the image of and taking Fk to be the image of the bounded idempotent Et of K, we see that T is decomposable. But also wanted to say that in the case of a decomposable operator, theorem, sorry, I'm a little bit exactly. Then the corresponding so T is decomposable, the corresponding spectral capacity is unique. So we write it as F is equal to F T. And in fact, has a description as a local spectral subspace. K is a local spectral subspace, which I'll define maybe not today. Which is traditionally denoted H sub T. I'll say what those are next time. So I'm out of time, I believe, for this lecture. Let me just say, so this is all, of course, well-known stuff, and I think classical maybe by point. So let me just say we have these ninth class of operators on D of H. We have the scalar type larger class spectral operator, spectral operators, and then decomposable operators. And they're all very interesting, and it's interesting to if you've got a particular operator to understand whether it might be in one of these classes. And the main results I want to present, building on some marvelous results of Ufaha Group and Anna Schultz, is that for this B of H, for elements of a finite mononomial more. Most of you probably know, but don't worry. I'll give you a definition. Finite mononomial algebra. We have something good, like we've got that always holds, provided that we back away from the spectrum a little bit and think about the sort of Brown measure. So Brown measure is a sort of spectral distribution measure that exists for all operators of it. And that will be where I start next time with Brown measure. So you take the spectrum and replace it by the Brown measure. And this can be used to investigate operators in all factors. Now, where is the free probability theory coming in? That is going to be a little bit. There's not a lot of it here, but actually some of the operators that we study using these techniques will be coming from free probability theory. And also, I should say, next to Schultz. Their group theory results, their marvelous results, involves probability theory in a fundamental way. To describe that a little bit. So I'll stop there. Thank you.
Can you show some example of the non-decomposable operators?
Yes, we will see a non-decomposable operator. And this will follow that we prove in the coming lectures. So we will see a non-decomposable operator here.
But it's correct to say that most operators are not decomposable. Is that correct?
Yeah. So
somehow like
we'll see a non-decomposable operator, but in B of H, what's the non-decomposable?
anything with an non-zero.
Unilateral shift.
So in the definition of scalar type, you demanded that the operator agree with this integral. That was like a norm limit. What if I just want like weak operator topology limit? Does that find me anything? Does that become a very generic thing or interesting?
I would presume. I don't know. I haven't investigated that, but I would presume that if you have the non-diagonal spectral measure and you have an integral in some sense, then it turns out to be a scalar type.
Any more questions? Speed again.